Hi everyone, I'm Jorge Delgado, as I was introduced as. So here I'm going to talk about more in the numerics. So yesterday mostly there was various talks about solutions, mainly Bose stars, for example. And one particular question about Bose stars, for example, or the solutions is that there is no way, at least so far, to obtain them analytically. There is no analytical solution for those solutions. So one has to basically use a numerical method. And one of the ways that we work, at least in our group, together with Eugene, for example, is by using this FIDISOL/CADSOL. So my idea for this mini course is that this first lecture will be more about the solver and how to use it, how to obtain the equations, how to put on the solver itself, then how to obtain the solutions in the end. And my second one will be more about what to do with the solution. So imagine that we have a solution that you obtain, and how do you extract physical quantities, like the mass, angular momentum, and other quantities. So let's start this first. I forgot to start this first lecture. So firstly, what is this FIDISOL and CADSOL? Essentially is a professional package written in Fortran, so it's like a Latin, so it's a very old type of.
Can you hide the bar, the default bar?
Okay, sorry. Thank you. So as I say, this package is written in Fortran, so it's like the Latin of programming language. And it basically can solve any non-linear system of partial differential equation if they are elliptical or parabolic. They have to be at least 2 or 3 dimensional, elliptical, parabolic, and can be subjected to any boundary conditions if you restrict them to a rectangular domain. Essentially, this solver applies a finite difference method for the discrimination of the differential operators, and use as well a root finding method, which is the NewtonRaphson method. You can also have a self-adaptive grid and a consistency order. Finally, the solver itself can also provide some error estimations for the cubic solution. So since, for those who don't know, I believe most of you probably know, so the NewtonRaphson is a method to find roots of functions. Essentially, it uses the derivative of the function. So here, and here we have a very small animation of how to do it. So essentially, you start with the initial guess, which is close to the root. Then you can take the function and its derivative to approximate iterativity to the root of the function. So essentially, in the end, what the solver does is more or less this, but a more complicated setup. Since the solver uses a NewtonRaphson method, there are some expected aspects that you have to be careful with. So firstly, you have to write your system of PDEs in this form, which basically you have a set of differential equations. So here x and y are the coordinates, for example. And here u is the function that we have to, or we want to find. Then this ux, uy, and u double x and so on are the derivatives of the functions in respect to the coordinates. So you write this, you put everything to the right side and say that that must be equal to 0. So that you can find the zeros of this system. You also have to provide the Jacobian for all the functions that you have. This is quite simple to do. You only take the set of partial differential equations and you do the derivation in respect to the function and its derivatives. So it's not very, very complicated. Then the most tricky part in this solver is the initial guess. So for some cases, some theories, you can write initial guess that you can use to obtain the solution. But there are some theories that sometimes are a bit trickier to find this initial guess. So for example, since here we want to find usually rotating spacetime, so 2-dimensional spacetime, you can use, if there is any, you can use the static limit. So you have a static limit without rotation, then you start to add the rotation to the solution and use that as an initial guess to go and find the others. Then you also have to provide the boundary conditions. So this is quite the usual thing one has to be careful with as well. And you also have to have a mesh with xy and xw, or x and y points. So how does the solver itself works? You start, as I said, with initial guess, so this U1, for which the solution does not solve the system of equations. It's not equal to 0, but it cannot be very far from 0, so it has to be a good initial guess. Then you introduce a new improved solution in this way. You essentially start with the initial guess, and you can use this. It's better. You start with the initial guess, and then you add some shifts, let's say, some variation to the solution, and you call this the new improved solution. And now, here you say, or you impose that this new solution solves the equations. If you do this and you expand this P of U to, if you expand in the W, so when you have small variations, then you can get, well, this expression, so it's a Taylor expansion. And with this equation, then you can you can compute exactly which is the variation that you have to do in order to have that. And you have now to use the original equation to obtain the new solution. So obviously, this is not entirely, it won't work exactly with one iteration. You have to do this at least 5, 6, 7 or more iterations, so that when the Newton's residual, so the P of U after n iterations, is lower than a tolerance that you can describe, then you can stop there the iterations. So basically, you start with the initial guess that is close, and then you approach the solution that you are searching for. Now, as I said in the beginning, this solver also can give you a narrow estimation of a solution. These are the Newton residuals, so how far does this quantity is different from 0 after n iterations. And also, it can provide the discrimination errors due to the discrimination process. So here, in this case, the solver uses a backwards finite difference method. Also, after you obtain the solution, you can also use some physical quantities for black holes. For example, you can compute the smart law, the first law of thermodynamics, and see how far are you from the real solution. Now, the well-known Kerr black hole, everyone knows about it, and everybody knows there is an analytical form for it. But here, what I'm going to try to explain a bit and to use it is, okay, imagine that Kerr never found this solution, never found the analytical expression for the solution. So what you will do? What can you do? So here, obviously, we'll start to use the solver. So now the question is, how do you start this process? How do you start from having a problem, a theory of gravity, where you want to find solutions, and how do you start from there and go all the way down until you find the solution? So, in the case of Kerr, which is quite a simple case, you can now start firstly to define an ansatz metric. So this is just a form that you will use to write everything, to write the metric, then to use it on the equations of motion, and to then input it on the solver. So the usual ansatz that we use is of this form. So here, in red, we have the ansatz functions. So F0, F1, F2, and W. We have 4 ansatz functions in this case. Then we also have this n, which is just a function that is found here in the right. And I forgot I have this. And then we also have this RH, which is in green, which will be an input parameter of the problem. So here, this RH basically is just the radial coordinate of the event horizon. So this is basically what I said. So although it doesn't appear, this metric can be connected to the Kerr metric, so this one. But it's not written in exactly the same coordinates, so it's slightly different. But there is a connection between this ansatz metric and the curve metric in biolinguist, which is basically just this, radial shift of the radial coordinate. So large R and large RH are the radial coordinate and the radial coordinate of the event horizon in biolinguist, and A is just the reduced angle momentum. So you can do this type of coordinate shift to obtain the curve metric in biolinguist. If you do so, you have this quite large set of equations. So you can write the F1, F2, F0, and W functions in terms of these large expressions. And then you get the care solution in biolinguist. So here it appears this the radial of the radial coordinate of the event horizon, and there is also this CT, which is just a constant. It doesn't have a transparent meaning, but at least you can say that is related with the rotation of the solution. Because if you compute the mass, the angular momentum, and other quantities with these expressions, you see that if CT is 0, J goes to 0, as well as the horizon angular velocity. So at least that we know. But after more than that, it's a bit difficult to understand exactly what is this CT. But basically what this means is that if you want to write the care metric in this ansatz metric, you just have to find or to use these expressions. Now, the first point is to have an ansatz. The second step is to define the boundary conditions. So the boundary conditions here for the Kerr case, as you know, the Kerr solution is regular outside of the event horizon, is stationary, asymmetric, and asymptotically flat. This type of symmetries will impose some boundary conditions. So for example, if you impose asymptotically flatness, this implies that Fy, so F0, F1, F2, W, as the radial coordinate goes to infinity, must go to 0. The axial boundary conditions imply that due to the axial symmetry and irregularity that, the theta derivative of the functions must be 0 at the poles. And then also, if you want to not have any conical singularities, you then also have to impose that F1 must be equal to F2 at the poles. This is not a boundary condition that we impose technically on the solver, but it's something that you can then use to see if the solutions are good or not. So it can be used. Then, since there is a Z2 symmetry on the equatorial plane, so the north hemisphere of the solution is the same as the south hemisphere of the solution, you can compute everything only at the region between the pole and the equatorial plane. And then you just say that the rest will be equal. And you also have to impose, in that case, the boundary condition at the equatorial plane that the derivatives of the functions, the theta derivative of the function, must be equal to 0 at the equatorial plane. Yes? Mm-hmm.
So, Jorge, about this condition of conical singularities, where does it come from? This F1 equals to F2?
So if you have the metric, you can then expand close to the poles, and you'll see that in order to not have any conical singularity, so to have a 2 pi rotation at the poles, the F1 must be equal to F2. You don't impose that exactly on the solver, but it's something that you can use to check if the solution is good or not, if it has a lot of error or not.
It's like a locally flat result, is it?
More or less. I don't remember exactly the computation, but I think that's more or less the same.
Okay.
I can talk with you afterwards. I have some notes about that.
Okay, thanks.
Then you can also go to the other boundary, which is the event horizon. And in this case, it's quite useful if you introduce a new coordinate transformation, this x. It's basically, instead of having the radial coordinate varying from the radius of the horizon up to infinity, you go from 0 to infinity. And you do this because if you now do an expansion of the metric functions at x equal to 0, so at the horizon, you can show, and I will show you afterwards in a mathematical file, that the expansions of the metric functions must go in this way. So with this you can impose very quickly that, for example, here this omega h is a constant and can be interpreted as the horizon angle velocity, so the rotation of the horizon. And with this expansion, you can write very simply that the radial derivative of the f function must be 0, and this w function must be equal to the horizon angle velocity at the event horizon. But this I will show you more specifically when I show you the mathematical file. Now, you have the ansatz metric, you have the boundary conditions. Now you just want, well, you have to have some equations of motion. So for the Kerr case, these equations of motions are the Vacuum-Einstein equations. So very simple, very easy to compute. And since we already introduced this radial coordinate, this x coordinate, it's better, and it would be better for the solver in the end, if you already use this x coordinate instead of the radial coordinate as in the beginning. So if you introduce this transformation, then the metric, the ansatz metric starts to be a bit more complicated, as you can see. So as these new two functions, h and s, but when you put this in Mathematica, it doesn't change much. It's just will give you the equations, and you just have to use them. So let's go to Mathematica, and let's see how you can how you can obtain the equations of motion. So here you cannot see very well. Let me zoom. Okay, can you see it more or less? Okay. Can try to put 3000, but yeah, here it will. Okay, so in this case, well, usually what you do, you start with Mathematica, you write the equations of motion, then you put ansatz, you get the final version of the equations of motion, so then you can use them to put on the solver. So here, it's got to be complete. So just to, this first part is just to clean some variables. So if you have been using Mathematica, just to clean everything. Then you can start to put the ansatz. So I start always to define the number of dimensions and some coordinates. Here I put the metric ansatz. So obviously here you cannot see everything, but you can imagine that on the right part there's the rest of the metric. And then you can just compute the inverse, the determinant, and the square root of the determinant. So this is quite standard stuff. Here, this part here, so these two lines, it just simplify a bit the notation, but it's not very, very, very important. And then you can do some prints to see if everything is fine. So you have the metric, the inverse metric, the determinant, and so on. So after that, you start with the Christoffel symbols. So again, you can write this very more or less simple. Basically, just do the sums and compute everything. Here, for example, I'll also use the symmetries of the Christoffel symbols, so not to use, or to use less resources. And if you want, you could, for example, here I have this comment, but you can remove the comments to see which of the Christoffel symbols are non-negative, and you can see the expressions and so on. You can then go to the Riemann tensor and do everything. This obviously will take a bit more time. It's more computations to do, but you can also use the symmetries of the Riemann tensor and do everything again. You can look then. So here you don't have to look very carefully to what I'm doing to specific computations. I will send you this at the end of the course. So if you want then to look more carefully what I'm doing and so on, I'll also send you some notes, some written notes where I explain more in detail what I do in every single step. So obviously I want you to stay to stay with attention here, but if you didn't understand something, then in principle it'd be written on the notes. So here, again, the same for the Ricci tensor, the Ricci scalar, and finally, I have the Einstein tensor. So in this case, for the Kerr case, this will be the equation of motion, since we then say that this quantity here will be equal to 0. Now, something that we do is instead of using the Einstein tensor in the covariant way, we use the mixed version. So one indices is covariant, the other is contravariant. And we do this because it's a bit simpler, the equation starts to be a bit simpler, and you can rearrange them to have more compact equations that the solver will also basically give you a better accuracy for the solution. So here we do exactly that. And in the end, if you want, this is not necessary technically, but if you want, you can also compute the Craftsman scalar. So here, this will take quite a long time because there's a lot of sums that we have to do, and usually, sometimes the mathematical file crashes when computing this, so be careful when you try to compute this. But here, you usually compute this quantity because it helps to see if there is some pathology on the solution. So if there is some point where the Craftsman scale diverges or something like that. Okay. Then here we also have the energy moment tensor, but since we are in Kerr, that is equal to 0, you don't have to use it. But usually, for example, for Kerr with scalar hair, then the energy momentum tensor will be non-zero, and you have to also use it and define the equations of motion with that. So in the end, what we have to do is to write essentially the equations of motion. Not here, no, it's here. So the only terms of the Einstein tensor that will not be trivial are six of them. So, and since you only have 4 functions, there will be six equations for 4 functions. So you have more more equations than functions. So you will write 4 particular equations for the 4 functions, and then you can use the other 2 to use as constraints. So basically, the solver will compute those 2 equations, and you will see if it solves the equations or not. But you will not use them to obtain the solution. So the four equations that will be used to compute the functions are these 4 in this particular case. So this is a combination of the Einstein tensor, and we do this because this way each equation will give you only second-order derivative for each function. So the first equation will only give you second derivatives of the radial and the theta direction for the f1 function, for example. The second one will give you the same, but for the f0, or the f2, sorry. Then the third is for the f0, and the last one is for w. And you do this because the solver likes it better this way, essentially. If you have only second derivative terms of one function in each equation, solver tends to work best in this way. That's why you do this rearrangement of the equations. So you can see that instead of you doing this combination of the Einstein tensor, you could use just the expression. So GTT, so for example, you could use just TT equal to 0, for example, or GT, no.
Like you're doing spherical symmetric.
Yeah, for example, you could use this. Okay. You could use this, but the solver, in principle, could also solve the problem. But for numerics and for accuracy, it's best if, instead of using this, you write each one of the equations, and each one of them only has second derivatives of the radial and the theta direction of only one function. So, for example, the first one will have a lot of terms, but the only terms that have second derivatives is only just one of the functions. f1, for example, for the first, or f2 for the second, and so on. And now, it's me, or I think it's...
So it appears...
that we lost connection.
Yes. So, not sure if it's the whole building or only... So it's supposed to be general, right?
Supposedly I have internet, but...
So we are still recording, so I think we should go on with that, but
I can
unfortunately...
But then I cannot show my slides. That's Sorry? Queres que comande? Ou- Os slides posso, mas depois tenho os matemática falso para mostrar. É mais esse problema.
So a technical problem right now, so you have to locally project the slides.
The problem... Ok, let me...
Mas aí não vai dar para usar o matemática.
Pois, eu tenho o PDF dos matemáticas, só depois tenho que pedir para trocar. Acho que precisar. Tem lá os... Era uma vez.
Why we try to arrange. So if you have this equation, one thing that you have there is that the radial coordinate r equals to rh should describe the horizon, right?
Yes, the horizon.
So
Yeah.
your coordinates somehow should be adapted to the black hole case.
Yeah.
Because it could be that the surface is not like
Yes. You could have a boson side, for example. You can use this as well, and I will show you that on the next lecture. But here I'm using that specific ansatz, so this one, because I'm trying to obtain the Kerr solution.
yeah, but
But-
for the boson, for the scalar, for the Harry solution, this is also true.
Yeah.
So is there a situation in which you have a deformed horizon? So for a deformed horizon, this shouldn't work, right? Because you have the horizon is not a regular r equal rh. So how would that change? How this would change the boundary conditions? So
Yeah, it
is there a
would.
way to account for this type of situation?
Well, technically, I would say so, yes, but it will be much more complicated. But in principle, you could find. I think I could find some way to write this in such a way that you can then use FIDISOL to obtain the solution. But it will be way trickier to do that.
Yeah.
So, for example, here we usually just use this to obtain stationary and asymmetric solutions, so everything is more well defined. But in the case where you have the form horizon or something more exotic, let's say, it will be more trickier. But I would believe that you could find some particular way to write everything to use the FIDISOL. You can also talk with Eugene. Right?
No, I was wondering if you.
But you can talk later about this. So,
Sorry, Jorge. So I because we cannot project your slides to the recording, so we will make with what we have now. So I will ask you to
Okay.
be a little bit closer from the screen because we are going to capture
okay.
the slides.
Mhm.
So thank you.
Okay, so as I was saying, you have 6 particular terms of the Einstein tensor that are non-trivial. So we have 6 equations for 4 functions. So you can write, or you can use 4 of them for the solver to obtain the solution, and then use the remaining 2 to use as constraints. And as I was saying, it's best for the solver if each one of the equations only has second derivatives, so the radial and the theta one, of one single function. You can have first order derivatives of all the other functions there, but the second ones will be only of one. So if you do that, you can find this set of combinations of the Einstein tensor to have exactly that. Then you have these remaining 2 constraint equations that then you use just to check if the solution is good enough. Now, I will show you another Mathematica file, but podes abrir o fecheiro PDF que... Então dá para...
Since we are now back with the connection, so
Okay.
I think we can.
It's a bit tricky to do this. Okay. Ainda está conectado. So what I'm going to show you now, when everything is working again, is the boundary condition. So specifically, well, first I can show you other thing. So what I'm going to show you on the Mathematica file are the full equations. So here we have the specific set of the full equations that you can write and expand everything just to have all the terms. And you can do this for all the equations. And in the end, you can print out those equations. So you can see here, for example, the first equation, you only have, you only have the second derivatives of the f1 function. So here you have the radial one, and then somewhere here, so it's here, the second derivative of in the theta direction. Then you have all the equations of motion that you want to put it on the solver. But now let me show you the expansion, so the boundary conditions. So here I will motivate a bit more why do we write specifically those boundary conditions. So if you do, let me take this. If you do a function around the horizon, so here again I just clean the variables. Here I'm just copying all the equations that I obtained on the other Mathematica file. And here we'll do the expansion. So in this case, you have to write what is the specifically functions for the h and the s that appear on the Danzat metric. And then you can do a type of expansion. So here, all the functions will depend on r and theta, but you'll do an expansion on the radial direction. You are on the horizon, you will expand on the radial direction. So you write this as a power series, basically. So in first order, or in a zero order, you can take the equations and do a series and simplify just to have a more compact way to see the equations. And in the end, you'll see that we have some results, but here it's a bit tricky to see directly. But at the end, if you look at all of them, these are the equations. So this must be equal to 0. So it's the equation of motion must be equal to 0. So all these terms must also be equal to 0. So if you take everything and you try to see which quantities must go to 0 or to have some particular value, at the end we will see that in the case of the W function, so the W function at the horizon must be a constant, and it will be the horizon angle velocity. And its first derivative, in order to the radial coordinate, must be equal to 0. So here it motivates a bit more why do we get those types of expansion when I talked about the boundary conditions.
When you calculate, when you use this code, and which kind of, how far you are from the horizon normally?
So here you technically at the horizon, and usually you'll just go to the second order. So
no, okay, but your RH will not be exactly at the horizon. It will be like an epsilon from the horizon normally, or you are exactly numerically at the horizon when you compute things.
No, technically you are very close to the horizon.
Very close.
Very
okay.
close, yeah.
So fixing that, how many orders you need in the expansion normally?
Yeah, usually you will go to only the first. The second one already starts to give an expression that's very, very large. You cannot take anything from there. So you'll go to the zeroth and the first. You get some results saying, okay, the functions must go in this way close to the horizon, and use that as the boundary condition. That's basically the
But
idea.
if I then impose your condition a bit farther away,
Yeah,
then
you can
you
do
will
that,
need more,
and then
right?
you can do a Series expansion up to infinity and get all the profile of the function. But here it's just very close to the horizon to see exactly what will be the boundary condition there.
So
you
it's 0, 1 normally.
Yeah, basically, yeah.
Thank you.
But technically you could do fifth, five,
Yeah,
and
sure.
go all the way.
For the quasi-normal modes, when you're imposing boundary condition oscillating waves, you might need 10 orders, 11 orders. So that's why I was asking. It's only first and okay.
But here, since you just want to know exactly, not exactly, but close to the boundary condition at the horizon, the rest will be the solver that will find the rest of the function. So here we're just looking very close to the horizon to see the boundary, which will be the boundary condition, then use that, fix that, and then the solver will get the rest.
And you impose regularity. This is a function that will not oscillate at the horizon, so also that probably helps.
Yeah.
Thank you.
Okay, so at 0, or you can see, well, these two conclusions. And then if you go to the first order, you can do the same, and since all of these equations must be equal to 0, you can then, at the end, say, for example, that the f0 function must be equal to the f1 function at the horizon plus a constant. This has to do with the fact that the Hawking temperature at the horizon must be constant. And then the first radial derivatives of the f functions are equal to 0. So that's exactly what we have here for the equatorial boundary conditions. So so here, the derivative must be 0. Sorry, not here, sorry. So the derivative must be of the f function must be 0. W must be equal to omega h at the event horizon. Then you can do the same for the poles. So you can again go back to grab the expressions and do now a Taylor expansion or power series in theta. And by doing the exact same idea, so the zeroth or approximation and then the first one. So for the zeroth, you have that the derivative of theta, of the function in order to theta, r of the f0 is equal to 0. The f2, the derivative of f2 must be equal to the derivative of f1, but on the first order equation we'll see that will be 0. And then here we have again the conical singularity. So f1 must be equal to f2 plus a constant, but since you don't have or don't want to have conical singularities, that constant will be 0. Then the first order approximation, as you can see, can already start to have large expressions. But from the other ones, you can then see that f1, or the derivative of f1 will be 0, so the derivative of f2 will also be equal to 0, and the same for the Dirichlet function. So here we have basically the, okay, here. So here we have this not here, here, these specifically boundary conditions that the derivatives of the functions in order to theta at equal to at the poles must be 0. So this motivates a bit more why do we impose these boundary conditions. Now, so you have the metrics, you have the equation of motion, and you have the boundary conditions. One problem yet we have to solve is the fact that the radial coordinate we're using so far goes from 0 to infinity. But usually computers don't like infinity. It's quite tricky to deal with infinity. So one thing you can do is to introduce a new radial coordinate, which is a compactification of the previous one. So instead of going from 0 to infinity, you go from 0 to 1. So that's what we also do. We introduce this x bar in this way. And now instead of doing everything all over again, you just have to change basically the derivatives of x. So you can do this transformation, and in the code you write this, and everything will be well defined.
Sorry, so you do that to deal with the infinity, not with the horizon, or you use the compact fire coordinates for the integrations overall, or?
So here is more just because of the infinite, because usually in biolinguistics, let's say the usual, the radial coordinate goes from the horizon up to infinity. Okay. Then you do one first coordinate transformation from going there to 0 to up to infinity, so that you can do expansion at x equal to 0, which is easier to do. And then you do this other one just to compactify the infinity to a finite value. So it's just to have a very well-defined limit.
But for the integration, you use the usual coordinates, or
well,
for the numerical integrations? Yeah.
No, you use this one.
You
basically, yeah. You on the solver, you, for example, the grid that you will use will be from 0 to infinity, not infinity, a very large number. But then in the solver, you take those values and you do this transformation. So the solver will use the compactified grid to do the numerical integration.
Okay. Okay, thank you.
Okay. Now, the last Mathematica file. So here we'll do the prints. So everything that we obtained was in Mathematica. And obviously Mathematica works very differently from Fortran, mainly in syntax. So we have to take everything that you got so far and write in a way that FIDISOL can understand, or the Fortran, the compiler. So you can do again, have all the equations. So for example, here we have all the equations again. But there's not need to show. And then you can do now some modifications so that the FIDISOL can understand what you are doing. So for example, FIDISOL uses this U1, U2, U3, U4 as the number or the name for the functions. So for example, in Mathematica, you use this label to call the functions, but in Fortran, or in this case in FIDISOL, you have to use these labels. So you can write everything, or rewrite everything. So here, for example, the radial derivative now will have this FF, which is essentially this quantity here. So this quantity here, this one. And you can write, you can write that, you can write everything in this way, so that when you print everything, you have everything written as Fortran wants. So for example, here, the h function and its derivatives, and also for the s, we write just a name, and then you define the name within the Fortran file, just to not have very large expressions. It's easier this way. Then here, for the trigonometric functions, we write the sine, cosine, and also the other ones in this way again, just to simplify everything. And then here we do the same for the expression, for the exponential. Then, For some real reason, which I think I know why, but Fortran doesn't like very large expressions. From what I remember from Philippe Freite, he said that this has to do with the fact that since the Fortran is a very old language, it's from the time that if you want to compute anything, you have those cards where you puncture the holes, and that will be the code. And those cards have a fixed length. So when you went from that to the usual now computer type of language, Fortran still has that that limit. So the functions or the equations cannot go above a limit. So in order to impose that, you say that your page for the output will have some fixed width, so that when you print everything, instead of having a very long line, you have some enters in the middle, basically. That's just because, well, it's Fortran. I think the new versions of Fortran doesn't have this problem, but since also the solver is a bit older, you also have to be careful with this. So now you can do, or you can print all the equations. So equations, all the rest. So here I have, for example, all the equations, the research scale, and so on. Now, there's also a missing piece that I mentioned in the beginning, which is the Jacobian. The Jacobian, as I mentioned in the beginning, is just the derivatives of the equations, so the set of equations, in order to the functions and their derivatives. This is quite easy to compute, but it takes quite a long time then to copy everything for the Fortran file. At the level of Mathematica, you only have to basically say that you want the derivative of the equation 1, for example, in order to the function 1 and its derivatives. So that's what we have here. You'll get quite small expressions, usually. For example, here we have some of them. But you have to do this for all the functions and all the derivatives and all the equations. So here, for example, you have for equation 1 and the function 2 and its derivatives. And then you have the same for the function 3 and then the function 4. And then you have to do exactly the same for the equation, the second equation, the third, and the fourth. So you can see that it starts to pile up a lot of equations. But you do this so that you then copy this to the Fortran file and everything is well defined. Okay. Now, let me show you so here's, let me zoom. Yeah. Not this one. What was? So the FIDISOL have essentially two essential files. The first one is the 2/cad.f, which is the brain of the solver. Essentially, what this has is a lot of subroutines that can be used to solve several types of differential equations. What we want to use is the one that solves partial differential equation in two dimensions and elliptical, and it will essentially be one of these routines. So this is the brain. Do not touch this file. If you touch, you probably won't. The solver won't work. So don't touch it. Then we have the V1.4. This is the one that you will have all the function, all the equations, and all things. It's here that will changes everything. No, sorry. It's a bit tricky to do this, but you can see it, more or less. Okay. So in the beginning, there are some parameters. So here, for example, that has to do with the solver. The ones that you usually change is either this nx and ny. So here, in the beginning. So here, for example, this is the number of points on the grid. So, for example, here you have 251 points in the x direction, or the radial direction, and 33 on the theta direction. This PD, for example, is equal to 6, so this is the consistency order of the discrimination. And another one that is quite useful to know is this Ilean 1, which basically is the number of the linear operation to reverse the matrices. But usually you don't have to change much in here unless you want to explore. Then there's a lot of functions that here you don't have to change. So here is where you start to change again the file. So in the case of Kerr, you have two input parameters. You have the radius of the event horizon and the horizon angular velocity. And here is where you define those values. You can, for example, here say that the radial of the horizon is 0.1 and the horizon angular velocity is 0.96, for example. Then here it's where the iteration begins. So the Newton-Raphson method, it's here that you start. For example, here in this case, we're only doing 3 iterations. Usually it's enough, but if you want a bit more accuracy, you can do a bit more. And after that, here is the code to run the solver. For example, here is where the initial guess it enters. So we have this file, this funct.t.data, which will be the initial guess. So we have to write the initial guess in this file, and it will read it, the file, and then use it as the initial guess for the iterations. Then it will do its work, and now we can ask where do you put the functions, where do you put the equations, where do you put the Jacobian. So that part is on the end of the file in these subroutines. The first one is where you put the equations, so the equations of motion. So here, for example, you can see that everything is defined with these labels. Here, for example, is the compactification of the radial coordinate. And here again is the definition of the trigonometric functions. So for example, here you also have the C and the H functions. And here is where you put the equations. The way you do it is essentially saying that equation 1, for example, you can call it equation 1, you go to the Mathematica file, you copy everything you put here. You can do the first, the second, the third, the fourth. And then this is where you say that these are the equations that you want to solve. So essentially, what you have here is saying that the Newton residuals will be equal to the equation. So you are saying the solver that you want to find the zeros of these 4 equations. So it's here that the solver will know, okay, these are the equations we have to solve. Here you can also put some parts of the energy momentum tensor, but since its curl is equal to 0, so it doesn't change anything. Then you have the Ricci, for example, and the constraint equations. So the first one, the second one, and this will not be solved. So this here is just, okay, the solver found the solution. It will replace everything in these equations and give you the output, and write this on some output file, which is, I don't know where it is. Maybe it's down there. So as you can see, the Crashman scalar is quite large. So it will be written here in a file which is t44.data, if I'm not mistaken. So this is essentially the first subroutine. There are 3 more. So the second one has to do with the Jacobian. The second one has to do with the boundary conditions. Sorry. And the way that Fortran usually likes to work is with this go-to function, where you have these 4 labels. So 10, 20, 30, and 40. These labels basically will go to the specific boundary conditions. So the number 10 is the boundary condition at the event horizon. So you have the 10 here, and it's the boundary condition at the event horizon. So the way that Fortran, or in this case, the solver uses or imposes the boundary conditions is similar to the equations. So basically, it's trying to find the zeros of those equations. So for example, if you have the boundary conditions at the event horizon, the derivative of the function is equal to 0, but the W1 is equal to the angular velocity of the event horizon. So in order to put that on the solver, you essentially rewrite everything such that it's equal to 0. So obviously this one is quite simple, but this one you only have to take from one side to the other and say that this quantity must be equal to 0. So that's what you do. Here, for example, you're saying that, okay, so at the event horizon, the derivative of the function 1, 2, and 3 is equal to 0, but the function 4, so it's the one for the w, is minus the event horizon angle velocity that we defined in the beginning, and this must be equal to 0. So that's the way you do or impose the boundary conditions on FIDISOL. Then you have here, for example, the boundary conditions at infinity. So this will be the label 20. So here you just say that the functions must go, all of them must go to 0. So just write that. Then you have the label 20, which is for the boundary conditions at the poles. So again, you write what you have to write. So in this case, that the derivatives of theta, all of the functions must go to 0. And finally, the final one, the number 40, is the boundary conditions at the equatorial plane. So again, you do the same. Then the third subroutine has to do with the Jacobian. Now that's the one. So it's here, the third one. This one has to do with the Jacobian. It's here that we'll put all the entries that you compute on the Mathematica file for the Jacobian. So as you can see here, everything that you obtain, we have to copy and put it here. So this is quite tiresome because that's a lot of equations you have to copy and paste. So sometimes it's a bit trickier. In the Kerr case, you don't have a lot of equations that are non-zero, so you don't have to change a lot. But for example, Kerr with scalar hair, you have much more lines that are, or quantities that are non-zero. But essentially, that's what you have to do. In the end, that's what you have to change. So subroutine 1 is for the equation of motion. You can copy from the Mathematica file and put it there. The second subroutine is for the boundary conditions, and you write everything in the way that it is a Newton residue, so it's equal to 0. And the third one here is the Jacobian. If you do everything right, hopefully, then you only have to run the solver. So we have two files, as I mentioned. We have the brain and the file that you change. So we have to compile the two. Firstly, you compiled the 2/CAD.f, so this is the brain. You compile it and you put this flag, this flag C. So this flag C basically says that you not want to link this file to an output. So it doesn't produce an output that you can run, that is, because it will give you an output. So when you run this second one is just optimization, but I found out that the iFortune already has this optimization flag enabled, so you don't have to put it. I put it there, but you don't have to. So if you run this, you get a lot of warnings. You run it, starts to get a lot of warnings. They are not very, very important, so you don't have to worry about. You only have to worry about if it gives you an error. If you give an error, it's trickier. But if it is warnings, don't worry much about that. Then you have to do the same for the V1 file. So you compile the V1 file with no link. And then with the outputs from this line and this one, you can compile the two outputs and then link the two outputs and create an executable. So here I call it the run car, so for example. And then you'll just have to write or to run the executable. Okay, so the executable, there are several things that will appear. Okay, let me, not here. So for example, firstly, we compile this one. As you can see, there's a lot of warnings. This will take a bit. After that, you compile the V1 file, and in the end, you can compile everything. So maybe I should have done that before explaining, but let's wait a bit. There's not a lot of time, but there, when you compile or when you run the executable, there will be an output that the solver will give you. And there are some specific parts of the output that usually are the more important ones, mainly the Newton residuals that should go very close to 0, as well as their estimation from the solver. I should have done this before. So, are there any questions so far? Yeah.
Thanks. In the file of initial data, what do you use as initial data?
Ah, okay.
I mean, can you use
Yeah. I didn't
Minkowski,
mention
for example?
Minkowski.
Or what do you use?
Minkowski is a bit trickier because, firstly, you don't have an horizon there, so it's a bit tricky then to jump to something that has an horizon. The usual, since for Kerr you already have an analytical metric, you can use that. So you can use those expressions that I show you for the F1, F2, F0 in terms of the CT and RH and so on. You can use that to obtain what is the values for those functions, F1, F2, F0, and W, and then use that as an initial guess. For Kerr, obviously, you can do this because you have the analytical solution. Another way that I mentioned in the beginning is try to use the static limit, for example. So in the Kerr case, you could start with Schwarzschild and then try to impose some rotation. So adding, starting with the horizon velocity as 0 and then increase slightly this quantity. And you start to have rotation, and then you can go up from there. Usually, well, some of the cases, that's what you want to do. If there is if there is already some solution in the static limit, you can then try to add the rotation to have the rotation solutions. Here in the Kerr case, since you have the analytical answer, you can use that. That's basically that.
And what about the grid?
The
grid has to be regular?
The grid usually, well, in this case, I already specify the grid, so it was those 251 points in the radial
but
direction.
it's also in a file, no?
Yeah, you can do. Because the way that usually you get the grid, for example, you use the compactified coordinate, so 0 to 1. You divide it equally in n points if you want.
In x and in theta.
Yeah, and then in the vertical axis, or the theta axis, you can just divide it, create some equal spacing between the points from 0 to pi, or 0 to pi over 2 in this case. And then you can use that, and you have to then to say the solver how many points you have, and give those grids. So that's the grid x dot data in grid y data that appears here. So I can show you. So these two files. So for example, yeah, it has a lot of numbers, but yeah. That's essentially that, yeah.
Okay, thanks.
Okay, so you are trying to obtain the Kerr solution, right? And so you assume some boundary conditions, you also assume the Eisenfield equations, but in this case you know that the Kerr solution is a solution of general relativity, right? So I was wondering about the possibility, for instance, you have a given geometry that you do not know what are the field equations that produce this geometry, and I mean, it would be possible, at least for the numerical point of view, to obtain the same geometry in distinct theories of gravity, but just change the boundary conditions that you are using.
Yeah, I say so, yeah. At the level of numerics, yeah. Okay. If you have a well-defined problem, with well-defined differential equations and boundary conditions, yeah, the solver doesn't care what you are trying to get. If you put that and it's well-defined, the solver will get you a solution.
Okay, nice.
In principle, it will. You can change it. You can change the boundary condition if you want. If it is Kerr, you have to impose this. Here, yes, I think it was in the case that we have
geometry,
a different...
not necessarily Kerr.
Obviously, here it's Kerr, you have to have those boundary conditions.
Yes.
So, now the brain was compiled. You can then compile the view 1, so this will be faster. And now compile the output. So it will be the brain.o and v1.o. And you can give it a name to the executable and run the executable. So here, let me go up. So here it's where the CADSOL starts to do its thing. Here some information about, for example, the grid points and so on, some quantities, but mostly, more importantly, are, for example, these residuals. So you can see it's already quite good, obviously, because we're using the care solution, so the analytical care solution. So the results are already quite good. But as you go further, there's some other, so here, for example, you can see how many steps the solver take and see some other quantities. So here we see that the residuals already are in the 10 to the minus 9, 10 to the minus 10 range. So this is again, so okay, it's still computing. This is only the first iteration. There are 3 of them that we say that we're going to do 3. So okay, the first one ended. So here, okay, the residual, as you can see, it's quite good. Then this is the maximum, not very important. But here is the relative norm of the error. So this is something that CADSOL does and try to see the normal error. And here, for example, for the equations 1, 2, and 3, or for the F1, F2, 0, and W, you can see the relative norm of the error is also quite small. And also, more importantly, it says that if everything goes well, you get this answer. So solution and the error estimation were computed. So in principle, everything went fine. If you have small errors and small residuals, and you get this line, in principle, you got the right solution. So here we start the second iteration, and exactly the same. So we will try to find a better solution. So for example, here the residuals are now 10 to the minus 13 and 12. So it's basically the same. Here we see that the norm of the error is more or less the same, doesn't change much. And at the end of the third one, which is still running, we won't get much better than this, essentially. Obviously, you could do more iterations if you want, but for this case, I think the best thing that you can get is something like this. So, okay, it's still running, but there's no need to show more. So in the end, here I have just, we'll believe that this is the solution that I obtained now. And you, obviously, since it's care, you can compare it with the analytical one. So here, for example, I have the F1 function. So although you probably can see it, this is the F1 function as a function of the compactified radius. So it goes from 0 to 1. And it's for 3 different angle theta's. So the poles, theta of pi over 4, and the equatorial plane. And then we have also the lines are the analytical function, and the pluses, crosses, and stars are the computed function. You can see that it's quite good. There's a good agreement, and to convince you more about it, not here, it's here. Here we have the absolute difference between the F1 function computed analytical and computed numerically. And as you can see, or probably can see because the labels are quite small, this is 10 to the minus 6 here, 10 to the minus 5, and 10 to the minus 4. So you can see there's quite a good agreement between the two, the analytical one and the numerical one. So essentially, that's it. That's what I want to talk about it in this first lecture. The next one will be a bit different, but let's hope it goes well, or it goes better. Thank you.
So due to the time constraint, we have time for one question from online. So since the local audience already asked a lot of questions, so I will ask you please to ask Jorge in the next lecture or during lunch and everything. So do we have some questions online? So Sergio, please just
So
hi.
I hope this time you can hear me.
Yes, we can hear you.
Okay. So thank you for your nice lecture, Jorge.
Thank you.
And my question is more about at the beginning of your talk, when you are showing the steps to obtain the numerical solution.
Okay.
And so I think it was in slide 4, if I read correctly. So how you define that, the value of that relaxation factor S, for instance?
So that relaxation factor is something that appears when you study the Newton-Raphson method, but usually that's only you put it equal to 1, generally. Even if you use it just to find a zero of a simple solution, usually they also put this S, this relaxation factor, equal to 1. But you can change it if you want. But what that means is that you can have larger or smaller steps compared to the initial guess. If you have a larger relaxation factor, there will be a large jump between the initial solution and the improved one. But if it is smaller, then it's a small step, small jump. But usually you just put it equal to 1. It's not very, I don't think it changes quite a lot, the numerics overall.
Okay, thank you.
So thank you, Sergio, for the question. So I think it's time for us to thank the speaker again. And
Thank you.